let's talk about databases. Right, so a database at its high level, conceptual level, is just a large collection of data. Right, presumably that data would be a structured data that follows some agreed upon structure. Right, that is not just a random set of pieces of data. Presumably they're data that somehow is related to one another, that you might have pieces of data that might be related to other pieces of data. A collection of fields can describe a particular idea, right? A particular related fields that might describe the idea of an employee, or might describe the idea of a product, might describe the concept of a course, and together fields will describe different aspects of that idea or that concept of a course, the concept of a student, the concept of a product, and whatnot. And those fields typically are strongly typed in that they are one of many available types of data. They're either strings or numbers or dates or Boolean or whatever abstraction we decide that is the indivisible type of data, right? That we are familiar with, right? We are familiar with characters. We're familiar with a collection of characters being a string. We are familiar with things being true or false. We have ideas of time and dates. We have ideas of numbers, and so those for us is the lowest level of abstraction that we can accept a piece of data, right? And it's kind of arbitrary, when we think about it, since underneath everything's zeros and ones, right? But since we don't want to think about that low level of abstraction of zeros and ones, we have drawn a minimum, right, level of abstraction that we like to build upon. We don't want to think about the details, so we've packaged all those collections of zeros and ones into various abstractions. Yes, and then we create even higher levels of abstraction. Right? If you group several zeros and ones, you get numbers. If you group several numbers, you get complex numbers. If you group complex numbers with names and whatnot, you get equations. And we can create all sorts of abstraction up higher and higher. So collections of fields, we call them records, right? So that's kind of a generic collection or bag of fields that together describe a particular instance of a class, of a classification, right? So one record might describe a particular student, right, or a particular course, right, or a particular product, but the whole collection of all the records presumably identifies all the instances of a particular classification of products, right? The abstraction of products, abstraction of students, abstraction of courses. Throughout the semester, we're going to be considering a running example throughout the semester that will talk about these abstractions: the students, departments, courses, sections, and enrollment. Some fictional university. And this is going to be our representation of that university. Okay, obviously the abstractions that we've chosen here presumably do not describe all the things that we could say about a university, right? But it is what we have decided to model, right? And the things that you decide to model are based on the things you would like to be able to do with the information. What kind of questions would you like to ask the database, right? And what you might want to ask for a given department: what students are enrolled in that department? What courses are being taught at that particular department? Which student is enrolled in which course, right? Giving a section of a particular course, which students are enrolled in which section, and so on and so forth, right? And typically, it is the questions you want to answer that drives the model, right? So that's very important, right? It's always the questions you want to answer that drives what it is that you're going to model and what the relationships are going to be, right? If you want to answer different questions, then you will need a different model, okay, and different relationships, right? So there's no one way of creating a model. There's no one right way. It only depends on what the kind of answers that you make, right? And some answers, I mean, some of the questions you might want to do, you know, if you just add a different verb or a different or something that used to be singular is now plural, then that changes the entire data model. You have to go back to the data model and, oh, I didn't know this was plural. I thought this was singular. Okay, and depending on that change, you have to go back and say, oh, I can't answer that. I need to add this additional table, this additional relationship, this additional constraint, right, for the data model. Okay, same thing. You know, depending on the domain. So the generic idea is that whatever domain, right, or whatever business or whatever problem you want to solve drives what the database you need to be able to answer those kinds of questions. Okay, here we have these 5 entities. That's a kind of like a generic term of a classification of pieces of data, right? So we have the student entities, the student department, the department entities, the course entities, the sections, and the enrollment, right? These could be represented as Java classes or C++ classes, or in a database as tables, okay? Or in an XML schema, right? And different instances of students, different instances of department might be implemented as Java instances, right? Or as rows in a database, right? Or as a document element in a particular XML document, or as a document in a non-SQL Node.js, MongoDB collection. Right? So this is a high-level conceptual thinking of what the different entities are, the different fields that might be contained in those entities, but it might be represented in a whole different way depending on what it is what that medium it is that you're going to store it in. Make sense? So first we're going to talk about it on a very high level, right? And then we'll talk about the different ways that you might want to represent it. Here we have different instances of these different classifications. We have 9 students. It's a very small university. We have across 3 departments. We have 6 courses. We have 5 sections, and we have several 6 enrollments. Right? And one of the things that you'll find is that each one of them has a unique identifier that goes along to each one of these records. Right? You'll notice that of those 9 students, you have one of the fields, right, is somewhat of an arbitrary, unique identifier. Notice that Joe, Amy, Max, Sue, Bob, they seem to have unique names, right? So we could perhaps use their names as their unique identifier. But notice that even though the data shows us that hints at the data being unique, it's actually not guaranteed to be unique, right? It is very possible that somebody has the same name as somebody else, right? So oftentimes we'll ask ourselves, is this data unique, right? And oftentimes the answer depends. The answer depends on the context. Is it just these 9 students? Then yes, they are unique. Is it within this classroom? Maybe we all have very unique names, right? Probably not. I'm sure there's 2 of you that have the same name within this class. Yes, but perhaps if you every time you broaden the context, right? There's less and less. It becomes more and more likely that particular field is not, or the value of that field won't be unique. Right? So oftentimes we choose an arbitrary field, an artificial field, right? That we can then guarantee that we're going to make it unique, right? We all have such arbitrary numbers that go along with us, right? We're kind of this cloud of unique identifiers that follows us around, right? We have the NEU IDs, right? We have social security numbers, we have our phone numbers, we have our bank accounts, So we're a collection of unique identifiers, right, that follow us around through our lifetime, right? And that is, you could say that is our identity, right? Our identity is like a cross-section of all these arbitrarily random numbers that make us unique, right? And presumably they are unique, right? And these numbers have evolved over time to guarantee uniqueness, right? Phone numbers, depending on your area code, they're unique within your area code. But if you go broader in international, it could be that you have exactly the same phone number as somebody else in another country. So we added the area code, the country code, right? And when Elon Musk gets to Mars, and we'll have phone numbers in Mars, we'll have to add yet another identifier, right, that makes unique across planets. Although, I don't know, you can have a phone call from Mars. Here you have a 30-minute delay time. A very slow communication. But nevertheless, right, the point stands, right, that we need some unique identifier. Oftentimes, the URL, right, the universal resource locator, right, presumably is this as the name stands, right, the name presumably allows us to universally address anything in the universe, right, if you keep adding, additional domains to it, right, oh no, there's no domain name for the US. We're very egocentric here in the US. We don't have a .us. I guess the US is the center of the universe. And then, but if you're ever anywhere else, right, you would have dot whatever, right, dot .it, dot .uk, right. At some point it will be, I guess, dot .mars. And as you extend the domain, right, we'll have to add more and more of these arbitrary identifiers. Right. So some of these are these identifiers. We refer to these identifiers as keys. Right? In this particular case, we give it an additional name. We call it a primary key. Okay, a primary key, not just a key. And what it means is that probably you'll notice that some of these values are replicated elsewhere in these other instances of pieces of data. Notice over here that. You'll notice that these values right here, 10, 20, 10, 20, 30, 20, 30, are actually taken from these primary keys that are there, right? And with the idea that the values here in these values here are referring to values that are in some other set of pieces of data, right? Meaning that presumably some of these collection of pieces of information are somehow related to data that is stored elsewhere. They're related, right? And that's where the R, right, relational, comes into play when we say relational databases, right? Is that we make an effort, right, to split the data across multiple classifications, right, and then say that that data that is stored in one collection of pieces of data are somehow related to data in some other collection. Okay, that somehow the record over here for student Joe, right, is somehow related to the computer science over here, this 10 over here, and this 30 over here for Bob, right, somehow related to drama. Okay, and you can keep following these things. Notice that these courses, right, course number 12 is being taught at department number 10. So computer science, we have a database system, you have compilers, calculus, and algebra. Looks like it's being are courses that are being taught in the math department, and that the acting and elocution here are being taught at the drama department. See that? All right, so somehow you have all these relationships that are being split across multiple collections of pieces of data, right? And somebody might say, well, why do we go to the trouble of splitting it up? Right? What's the point of doing that? Can't we just use one big Excel spreadsheet and put all the fields in one large spreadsheet and just have it all in one single place? Why bother splitting it up into 3, 4, 5 different places? That makes it very inconvenient. Especially if you write a form, for instance, on Google Forms, say, right, and you shoot that form across to somebody to fill out, right, and they fill it out, then you can then open that as a spreadsheet on Google Sheets, yes, and you would have all the fields in one single spreadsheet, very conveniently in one single place. So that's not split across because you have one form to fill out. Okay, but if you start looking at the data that you collect, you'll notice that a lot of the data keeps repeating over and over and over. Okay, and one thing I hinted at earlier in my introduction is that that redundancy, when you see a lot of repetition of the same pieces of data over and over and over, right? That's kind of hinting at you that maybe the is it okay that you have all this repetition? Maybe it's okay. Notice that we have some repetition. Notice that we have 10 over here being captured multiple times. 10, 10, 20, 20, 30, 30. Is that bad? Right? So typically the repetition is an issue when it's being repeated on the data that is being collected on. Right? For instance, in student names, the titles of the courses, and things like that, the names of the departments, on real data, right? Data that you actually collect, right? As opposed to this data over here. This data over here is not actual data that you collect. This is data that is arbitrarily there to do what? To create the relationships between the records, right? That is only data for maintaining the relationships of the data. It is not real data, right? It's nobody's first name, nobody's email, right? Nobody's last name, right? That's real data that represents something in the real world. Yes? All this other pieces of data is additional data that is used to maintain the relationships between the records. You see that? So these tables, these records, are always going to have a collection, we're going to have most of the data will be real data that has some representation in physical phenomena, right? But some of the data will be just for administrative purposes, right? To keep track of the relationships. Make sense? Right? So what we're trying to do is whenever we see redundancy in actual data, right? That should scare us. It says, oh, maybe there's something wrong with my data. Why am I collecting last names over and over and over? Why am I collecting at the same address over and over? Say you give out a form to fill out to folks that are walking out of a mall, right? And you're filling out a form, and people filling out a form and whatnot, and you're very likely to have unique folks filling out the forms. But say a family comes by, right? And so there's 5 of them in the family, and they start filling out the forms, right? And they're all typing out the same last name, right? Probably the same address because they all live in the same place, right? And so that is a problem, right? That you're collecting the same piece of data over and over. You're introducing redundancy into your data, right? And that should scare you as a data analyst. It says, I'm going to have problems with this, right? Because at some point somebody's going to move out from that family, right? And that address is no longer going to be valid, right? Or the whole family might move away and move to another place, right? And somehow I'm going to have this redundancy that is not valid multiple times. If I have to fix it, I need to remember that I need to fix it for 5 folks, right? And that makes it much harder and prone to error, right? That I have 5 pieces of bad data, right? That I have to fix 5 times instead of I fix it just once. Okay? I could inadvertently modify one but not the other, or I might forget to modify one, right? I might modify 4 but not the last one. Yes? And I'm introducing inconsistency into the data, right? As time passes by, data that used to be synchronous, right? That used to be valid, that is redundant, at some point it starts to deviate and be inconsistent. Right? What do you mean they don't live in the same place? What do you mean they live in the same place but they have different addresses? Right? So the data loses its value as you introduce redundancy and you introduce inconsistency. So to fix that, this is why we do this. To fix it, we normalize the data. Right? We split up the data in such a way that is represented only once. If you're going to capture the same address 5 times, well, you're doing it wrong. It should be one single. You should be captured only once, right? In a record that represents the data only once. And then other folks can refer to it saying, hey, we all live at the same place. We all live at the same place, right? And when you're going to change it, you only have one place to change it, right? And so you minimize the tendency to be inconsistent. Right. So we're going to be we're going to be having this running example throughout the semester. We have a university database where you have the student table or collection of pieces of data represented by the student. And you have records that each record represents an instance, right? An instance of an individual student. Enrollment, you'll notice that enrollment over here mostly has most of its content, right, is not representing real data. Okay, notice that we have these unique identifiers here for the enrollments. We have these keys over here that are referencing to a particular student, right, and referencing a particular section, saying that this particular student is enrolled in that particular section. So this kind of is playing the role of a map, right? It's mapping records. It's associating records that live in one collection, one table, right? It's associated to records that live in another table, right? We oftentimes refer to it as a map. It's a mapping table that maps records from one table to another table. We do have one field that is recording real life piece of data, right? Like grades, right? Oftentimes we refer to this as an association. We are making an association, and we're describing that association that this student got an A in this section, right? It's creating that an association. If he didn't have this field, typically we refer to this as just a plain old map, a mapping table. Okay, it's just creating associating records with other records. Over here, it's a association. So yeah, so enrollment is a map. We have a course. Notice that course might have several sections. And notice that you have DB systems, compilers, calculus, algebra, and you have course ID 12. Notice that we have two sections for that course, both of them being taught by Alan Turing. We have Newton is teaching calculus, and Marlon Brando is teaching elocution. Okay, so you have multiple sections of the same course. So the act of deciding, which tables are you going to use, what are going to be the fields that are going to be in each table, how you're going to keep track of the relationships between between those records. So those steps of deciding what that's going to look like is the act of designing. We're designing a database, right? So that's going to be the first week or so. How do we decide to break it up this way, right? And there are certain aspects and techniques of deciding how is it that we came to the conclusion that this is indeed the best way that you could represent the data. Okay, the choice of the name of the table, the choice of the fields, the choice that certain things are strings, certain things are numbers, certain things are primary keys, certain things are foreign keys that are referring to other folks out there, right? That we refer to that as the schema, right? The schema that defines defines the table, right? And so, and when you represent a model, a data model, using a schema, we call it the relational schema. It's a relational schema, okay? Or the relational model, right? Because it's represented using relationships. All right. Unlike if you would be using Java classes. If you're using Java classes, there are no such things as relationships, right? You would have instances of objects containing instances of other objects, right? Or pointers. If you're using C++, right, you would have all sorts of pointers going everywhere. Another aspect important in that distinction on whether you are representing it using a language, a programmatic language, or you're representing in a database, is that they're both are trying to solve different problems. One of them, the database, right, is trying to solve the problem of storing lots and lots of data, terabytes, gigabytes, huge amounts of data, right, for long-term access, right, long-term manipulation of that data, right, and that has its own challenges. Whereas if you're trying to represent data in a program, Java, C++, whatever, right, that data is by definition going to be very transient, right? It's going to live for a very short amount of time. As long as the program is running, it's going to live. It's going to have the data in RAM, right? And typically, it's only going to be a very small snippet of the entire data set, right? That you're ever going to be working with. Typically, will be at most the data that you could possibly display for somebody to manipulate. Perhaps 10 records at a time, yes? But at no point in time will you ever have the entire data set instantiated in RAM, right, as the program is running. It just makes no sense. So you only ever have a snippet, a subset of the original data set. Whereas a database, right, it has to deal with the entire data set. Okay, so whenever you're querying data, you're querying the entire data set, right, all the records. Right, so they're designed to deal with entirely different problems. Right, so some of the characteristics of a database system is that it's persistent, meaning when you shut off the machine and you come back to it, when you turn it back on, the data still has to be there. Right, so it's for long-term storage. Right, it has to survive a crash, has to survive a shutdown. Perhaps with multiple backups and whatnot, it needs to be able to store large, huge amounts of data, and even though it's huge, it should be able to manipulate that data, even though it can grow fairly large. One of the things that I noticed today, dealing with Mongo, is that when you're dealing with large amounts of data, for instance, I was trying to iterate over 86 million records. So I said, well, okay, well, I'll paginate and I'll consume it, 100 records at a time. And that's fine for the first 100,000 records. After that, the skip, that you skip to, 100 records or 1,000 or 10,000 records starts to degrade. The performance starts to degrade. It just starts to get slower and slower and slower. So because of the way it's implemented. It actually iterates over the entire data set until it gets to that record, and then it returns how many records you need. It's very, very, very slow and absolutely useless, to iterate over millions of records. So there's we're looking at different ways to work on that. But yeah, so databases should, if you have millions of records, it should still allow you to manipulate it, right? To access the data that's there. It would be useless if it has all the data, but you can't access it. It should be shared, meaning you're going to have, it should support multiple users logging in, adding, retrieving, updating, accessing the data without degradation, and with making sure that your folks are not trampling on each other, right? If I'm reading something, you cannot be writing to it. If we can all read at the same time, that's fine, right? But if somebody is reading, anybody who's trying to write should wait a minute, I'm reading, don't trample over it. Okay, I'm not done. All right, so there should be some traffic management there. It should be accurate. There shouldn't be any inconsistency. That if I deposit $100 and I'm transferring $100 from one account to another account, that all of a sudden somehow my $100 were missing, right? That I withdrew from one database, from one account, and I tried to deposit it to the other account, and somehow the database crashed, while my data was in flight, right? That somehow I lost my transaction. So it was, somehow it was recorded that I withdrew, but it was not recorded that I deposited. I said, wait, what happened to my $100 that I was trying to transfer? So certainly being able to recover from such problems such as that, obviously usable, have some kind of interface that will allow you to use. The database administrator responsible for the health of the database. So anyway, so how do we store the data? How is that we decide to store the data? Typically, most vendors will have their own proprietary binary representation of their data, typically in some heavily compressed manner to manage the amount of storage that they need. And usually you might have either in a single file or more typically what you'll find is that databases will keep track of your data into multiple files, right? They break it up into multiple files, and they'll have even auxiliary files, right? That will allow them to retrieve data in all sorts of ways, right? For instance, what is the best way to store data in a phone book? So typically you might say, well, I'll store all the numbers and phone numbers, last names, addresses in that phone book, right? But then I might say, well, in which order are you going to store it? So, then that's a tricky question, right? Because it depends how you want to retrieve it, right? Typically the most useful use case is that we store it sorted by last name, right? Why? Because, well, that's the most common use case, right? I know somebody's last name, right? And then I use binary search to search through the through that. Imagine somebody says, well, then I'm not going to sort it. I'm just going to put it in there, just in random order. Okay. Then how would I search through that? I would have to use linear search, right? That's the only way. I have to read through every single last name to look for it. So typically I store it to optimize the way that I want to retrieve it. Right, so first I need to want to know how I want to retrieve it. Then I decide how I store it. Okay? And we'll see later on, that's called indexing. Right? We decide how to index the database, right, in such a way that will optimize for the time that we want to retrieve the data. So typically a phone book, we index it by last name, right, so that we can then apply binary search, right? So we start in the middle, left, right, left, right, left, right, until we find it, right? But if somebody comes and says, well, no, I don't have last name. I actually have the phone number. I just don't know where they live. Okay? I forget their last name. Somebody called me. I have their phone number. I don't know who they are. Right? Is that phone book useful to me? It's actually useless to me, right? I'm just going to have to use linear search, so that I can compare every single phone number, right? So if the question was that I want to search it by phone number, then I would need a phone book that is now sorted by phone number, right? That it's indexed by phone number, right? And those kind of decisions, right, on how is that I want to store it, always comes on what is that I'm going to store, how I'm going to index it, how I want to retrieve it, and I might have two versions of the phone book, right? One if I have the last name, and one if I have the phone number. I'm indexing. I have two indices on that phone book, right? Right. So same thing here. Typically you will have a file or set of files with the original data that you inserted, right? Plus you'll probably have additional files, right, that will have references into that original piece of data, but they're sorted, right, by the particular field that you want to retrieve it by. Right, so if this were a phone book, you will have perhaps an original phone book, presumably not sorted in any way, and then you have two index files, one sorted by last name, one sorted by phone numbers. Right, so you might have multiple files, original data file plus multiple index files that point to the original data file. Right, so multi-user access, we need to support the multiple users accessing the data at the same time, making sure that we are managing the traffic and making sure that we are not allowing any inconsistency. For instance, when multiple people try to book a flight, right, and they both query for a flight between Boston and Chicago, right, and it comes out to you have 40 available seats, right? And typically there's a timer that goes along that says, yeah, this is true for the next 30 seconds, right? Because you have several other hundred or thousands of folks asking the same exact thing, right? And then it might be that by the time you decide where you want to sit, right, or you want to book, there are no more flights, right? Or the price has increased, I'm wondering if they have this algorithm that they see that it's me, the same person who's accessing, and they bump up the price, and it's still me. Anyway, when there might be some inconsistency, that whatever data that I have or that I'm consuming as a human being might already be stale, right? That underneath, right, the data is changing, and I'm only ever seeing a piece of data that is already stale. Right? By the time it gets to my screen, right, all sorts of things might have happened already in the database, right? So we have to put in some mechanisms that allows us to reconcile, right, some of that inconsistency, right? Whether we put a timers or we lock, we have some mechanism that we lock the data, and because I'm looking at it, no one else can look at it, right, or no one else can touch it, right, so that we don't go into an inconsistent state. Okay. Concurrency management, we need to be able to come up with policies that allow us to balance, right, the multiple threads, multiple processes accessing the same data, but at the same time, providing concurrent access. And databases need to be able to detect any conflicting data, right, and to be able to resolve policies to be able to resolve those. Typically, you have transactional transactions allow us to do this, right, and decide what level of transaction do we want. Do we want to use a policy that is very pessimistic, right? In a pessimistic policy, we say that, hey, if I'm accessing the data, I'm going to lock anybody who wants to use that data first, right? Because I am busy, I'm working on this document, and nobody else can look at it until I'm done. And when I'm done, I'll release it, and then somebody else can come in. If anybody comes in while I'm looking at this, they're going to be in a queue, and they're going to have to wait their turn, right? In a pessimistic locking policy, that's what would happen. But then you suffer the multi-threading, all the multiple threads running simultaneously. That performance gets a big hit, right? Because everybody's locked. Everybody's kind of waiting for this resource to be. It's kind of like a printer, right? The printer is there's no way that a printer could print 2 documents or 3 or 4 at the same time, right? It can only print 1 document at a time. Everybody else is in a queue, right? But what if I was only reading records that were towards the bottom? Why are you going to lock the entire table, right? So there are policies that are not as pessimistic. You have in the other extreme, you have optimistic locking. That means that everything goes, right? I'm not going to lock anything. We're going to instead use mechanisms that are social mechanisms that, over the wall, you say, hey, I'm editing this document. Don't touch it for the next 5 minutes, right? That's kind of like a social solution to the problem, right? We come to an agreement. We use maybe some check marks that I'm busy, right? And you agree not to touch or stay out of this area, right? In that way, you're kind of like what you do in Google Docs, right? I work over here, you work over there, and we agree not to trample on each other. Or that's kind of like a social engineering, some social mechanism that allows us to have the best of both worlds. So we'll look at transactional updates and transactional policies that allow us to implement these kinds of mechanisms. Then the database needs to provide some mechanism of handling authentication and authorization, right? Meaning, who should have access to this data, right? We have to have a means for logging in and knowing who you are, and once we know who you are, we need to have some mechanism of deciding now that we know who you are, what can you do? Can you read that information, that confidentiality, that this piece of information, or are you not allowed to touch that information? Can you read but not write? Okay, what kind of access do you have to pieces of information? So what kind of privileges do you have? So databases need to allow that. Also, memory management, right? One of the most expensive, the most expensive actions of a database is to actually read the data, right? Reading, right, or going out to the disk, right, from memory. So here's your database management system, some software that's running, and at some point it needs to read the disk, right, and reads data from the disk. That is many magnitudes slower, right, than whatever CPU is running. Right, so any operation you might be doing in the CPU will be thousands of times faster than a mechanism of reading an actual file system, right? So whatever the database can do to minimize the time that it goes out to read to the file system, the better. So typically what database systems do is that they won't just go out and read a single record, right? Even if they just need one single record, they'll probably just copy an entire chunk, right, of data and bring it into RAM, right, into fast RAM, right? And in the hope that the next couple of selects or the next couple of reads will be in the same block of data they just read, right? So that it would minimize the amount of time that it needs to go out to database to read the actual data, right? So we'll have some caching mechanism, right, that will read a lot of data and cache it in RAM to minimize data I/O. Okay, and this intuitively works, right? But depending on the indices you've chosen, right, and whether you chose to index something by last name or index it by phone number, right? That access to the database might be optimized or not optimized. It might be that if you use one index, you'll get one performance, but if you use another index, you'll get some other performance because the data might be naturally sorted in a particular fashion, right? And depending how it's naturally sorted, right, if you're accessing it by the index of its natural sort, you'll get a lot of performance. But if you're accessing it through some fields for which you don't have an index, then that caching actually will work against you, right? So you're doing lots of I/O, and all the blocks that you're bringing into RAM actually are worthless because the next read will not be in the block you just read, right? Okay, so we'll talk about this when we look at optimization a little later and indexing. Memory management, again, making sure that even though you might be reading something from memory, you might have many different processes reading from memory, and each one of them has the risk of being stale. Right? Once they read it, they're not accessing the actual data that's stored in memory. You have other folks reading and writing, and you can have all sorts of types of inconsistencies, phantom reads or queries that you made that are no longer valid, right? If you've admitted just a few seconds a little later, right? So we'll take a look at that. So data models, as I mentioned earlier, there are different levels of abstraction, right? You have the lowest level of abstraction, you have just zeros and ones, right? And on top of that, you have a file system. And on top of that, then you might have you start having kind of like conceptual models, right? Such as, under the files, on top of the file system, you might have a cache system, right? And on top of that, you might have some binary or tree structure, right, that represents on how to quickly retrieve the data using binary search, right? And on top of that, you might have the actual tables, right? That is a high level of abstraction. And on top of that, you might have even higher levels that might represent the data depending on how you most commonly retrieve the data. So because the decision on how you split up the data and store it on multiple tables, the original intent was to reduce redundancy, right? To minimize the risk of inconsistency. That was the original intent, right? But as we mentioned earlier, it might not be the most convenient way to consume the data, right? If you have a particular data model that represents students and sections and courses and everything, right? If you are a faculty, you probably just care about your sections, right? If you are a department, you typically care about across courses, right? If you are the registrar's office, you typically just care about across multiple departments, right? So depending on who the audience is, right, each one might want to see the data the way they want to see it, okay, or organized in a particular structure. So you have this competing, this competing goals, right? Of yes, I want to maintain, but I want to remove redundancy, I want to remove inconsistency, but I want to consume it in a convenient way, right? As a registrar, it's very inconvenient for me that you have. I'm sorry. As a department head, it might be very inconvenient. You have all the grades and all the students spread across. I have to go to this. If I need to know, how they did in this particular course, I need to go to the section and then to the enrollment and then to the students. I have to visit 3 or 4 different tables, right, to reconstruct the idea, the data, to then give you a report. It's very inconvenient for me. It would be nice if it was just one table, yes, that shows me the course, the section, the students, and their grade. Right? But that's not how it's stored in the database, right? So database typically provide additional, well, obviously the physical file system, the physical model that is represented in zeros and ones in the file system, but they'll also represent it in, where is it? I was ahead of myself. Okay, this one, the external schema representation, where you have the conceptual model. This is how we decided to break up the data, right, and all the relationships. But depending on the audience who wants to consume this data, we might reorganize it. We might create what are called views or virtual representation of this data that combine the data and into convenient collections like student course and student info. So for instance, the student course might combine data from the student table, from the enrollment table, from the section table, from the course table into one convenient student course view. Right? These are virtual views that look like tables, but they're not real. Okay? So most databases allow you to have these external schemas that just make it very convenient for the various audience. Right. So we might have, as we decide the level of abstraction, we might decide that we want to retrieve the data, right? Whether it's in some comma separated value format or whatever we decided to organize our data with, and you might start by writing C++ code or Java code or .NET code, and where you literally with low-level file system I/O, you read this data, right? Once you've done a couple hundred of these data access, you'll notice that there's a pattern in accessing this data. If you just knew the name of the file, and if you just knew what are the fields that you care about, right? If you just knew the fields that you want, if you just knew where the file was in there, if you just knew what the criteria of retrieving the data was, right? If you could parameterize that, right? If you could parameterize these things, as in the name of the file or the collection or where the data is stored, and what is the format that is stored, and the fields that you want, and the criteria by which you're comparing and extracting this data, and then returning a result set. Once you've done a couple hundreds of these, you'll find these patterns. You know what? I'm tired of writing this. You'll parameterize it, and you'll write some API that looks something like this. You know, that gives you a high-level language that allows you to parameterize the fields that you want, parameterize the data set that you're trying to iterate over, parameterize the criteria by which you want to search the data, right? And underneath this high-level pseudo-English instruction, there's a loop behind this, right? You know, somebody's actually reading a file, and it's extracting these fields, and comparing each one of those records against this parameterized criteria, right? And the records that meet that criteria are being extracted into a result set, right? And this comes back as a result set of all the records that meet that criteria. That predicate is a predicate, right? So if this is true, then you retrieve it. Underneath of all, behind this, there's an actual loop, right? Somebody is actually going through each record, right, comparing each record against that criteria. The ones that match are being added to a result set, right? And the ones that are not are just skipped. Okay. Now, how fast is this? Well, it depends, right? Depends on if I'm indexed by graduation year. Maybe if it's indexed by graduation year, maybe it's already sorted by graduation year, right? If it's true, it'll be very fast, right? I'll probably know where to start. Okay, I'll probably go through all the graduation years 1997. Once there's no more 1997, because it's sorted, I know there are no more years 1997. I'm done. But if it's not indexed by year, I will have to iterate over the entire data set. You know, from the beginning, first record, all the way down to the very last record. Yes? So indexing obviously plays a part into how fast, performance of this query is. Okay? Now, obviously, this the relational data model is just one of multiple ways that we can think how we structure our data. You know, it's only one idea, and it's predicated on the idea that we have relationships. We have records. Each record can refer to another record, and that at some point we need to reconstruct the data by joining records from one table with records in another table, the ones that relate to one another. But certainly there's graph-based models, there's object-oriented models, there's hierarchical models, and we'll visit some of these. Certainly object-oriented models when we talk about Java, we'll look at those, and hierarchical models when we talk about XML a little later, right? They're just different ways of thinking about how to structure your data and represent your data. Physical independence, again, these abstractions, what they try to do is to become independent of how actually you're storing the data, right? I don't want to know about the zeros and ones in the file system. Just give me SQL. You know, it's a high level. Or if you don't want to see SQL ever again, you can use JPA, you know, Java Persistent API. Right? If you want to treat it as just a plain objects, right, and objects containing objects, arrays of objects, right? You can think about it at the high level programmatic way. Right? We'll talk about that a little later. All right, let's take a break, and we'll come back right after these messages.